Hello everyone, in this video we are going to learn another lecture on the graphs. We will focus our attention on the introduction to graph property and graph representation using either array or linked list. And actually in graph there are many nodes, so we sometimes call it vertex, and they are connected by edge. So as we have learned from the recent lesson about tree is a kind of special form of the graph. In graph it is a general form, and there are many problems that can be solved using graphs. So this is the outline for this lecture. We'll firstly look at the definitions. What is graph? Next, we'll work on the terminologies term. What are terms that are used in the graph theory, as well as how we can represent graphs. And last but not least, we can have some practice on how we represent graph using various methods, including array or linked list. So graph is basically a nonlinear data structure that are consisting of nodes, or we sometimes call it vertex. In the singular form is called vertex, and they have nodes and edge. Edge are connect a node together, and as we can see on this picture, we have 5 nodes, right? We call 5 vertices, and the number of edges in here, because in one node through another they are aligned, right? I will call sometimes edge or arc is fine. It's a line connect one vertex to another vertex. So in here we have 5 nodes, and we have how many edge here? There are 7 edge, right? Because they are connected to each other. So in general, the set of edge describe relationships among the vertices, and we sometimes say the cost. For example, in the some problem that the distance from one point to another point, we can put the number on the line here, which describe relationships among them. And a graph G is defined as follow here. As we can see, we have G equal to V comma E. This is a set of vertices and edge that are combining together, that are constructed as the graph. And here's an example of a graph. We have 5 vertices, which is number 0 until number 4. 1, 2, 3, 4. And talking about the edges, we have 0, 1. From vertex 0 to 1 here, this is one edge, and we have another 4 edges by connecting them together. Actually 5 more here, so in total we have 6, right? 0, 1, 0, 3, 1, 2, 2 to 2 itself, 4 to 3, and 0 to 3. So in total we have 6. So there is a property saying that when x and y is an edge, we can say that x is adjacent. Okay, the word is adjacent to y, and y is adjacent from x. So we say x blah 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 to y, and y something from x. Okay, so this is adjacent. 0 is adjacent to 1. 1 is not adjacent to 0. 2 is adjacent from 1. Okay, because we have the direction, right? The orientation, the arrow here, we can say that. And I'll take a look on this graph. How many vertices and how many edge of this graph? We have vertices A, B, C, D, E, and F, right? So in total there are 6. And for the edge, we have 1, 2, 3 here, 4, 5, 6, 7, right? There are 7 edges So in graph, we are divided into two main graphs called directed graph and undirected graph. In the undirected graph, it normally consists of the edge that are called undirected edge. There is no direction at all. With the connecting from one node to another node, there is no direction. And about the directed graph, sometimes we call it the graph. Okay? The graph, and it consists of the edge that are directed. So as you can see in this picture, when we have two vertices here, okay, U and V, so the line connecting them together, there is no direction, there is no arrow, so this is called undirected edge. And in directed graph, all the edge here are undirected. However, in the directed graph, we have the arrow here from connect from one node to another, and to construct the directed graph, all edge must be directed. And sometimes we also have the weight. Okay, this is called the cost, or sometimes we call it distance from one point to another. So the weight graph here is a kind of graph in which that each edge it carries a value. It means that it holds some value, connect from one node to another. For example, in this graph, it shows the distance from one location to another. For example, from Dallas to Washington here, the value distance is 130. It could be mile or kilometer, depending on our measurement. So we can see that there are many connections from one to another, right? This is one example of the weight graph, and it also mainly used in the graph Google Map. For example, there are many locations set from one point to another, right? And there is some estimated distance from one place to another. So we'll see the application that use graph. For example, in the Google Maps, it extensively uses graph to indicate many directions all over the world and different local country as well. And based on the graph representation, it allows to map from one point to another with some distance. Although it's not really accurate 100%, but we estimately approximate the value as well to get the similar value. And another application in social networking site, they use graph to represent the network of people, the relationships among them. For example, Mr. A is a friend of B, and B has some friends, so A can connect to the friends of B as well in order to make more relationships and communication. And it also used in the network graph, or we call sometimes it's semantic graph, or even to help represent the flow of computations. Normally in the semantic graph, it describes the meaning from one thing to another, and based on the graph representation, it allows us to to get more facts and value from one point to another. And another thing is on the optimization on the database optimization language, because for some table to another there are relationships among them, and we can also represent them in graph. And the weight of the graph in the edge here can representing something like the verb or whatever that you want to describe them from one to another. And here are some more applications that adopt graph for the implementations, including modeling, representing the map, finding the path, the certain path from source to the destination. And we have another relationships representation as like a family tree, business, and family, business, military organization, and scientific taxonomy, and then some other complex activity as well. And next we'll take a look on the term used in the graph. The first one we call adjacent node, which are referring to the two nodes that are adjacent. It means that they are connected by an edge. When there is a line connect two nodes together, we can say that they are adjacent. So 5 is adjacent to 7, and 7 is adjacent from 5 because we have the direction here, right? You can read from the direction flow. And we have another one is called complete graphs. It is called when that every node or vertex, they are directly connected to every other node. It means that they are all connected to each other. This is called complete graph. And next we have the degree of a vertex. It is called the number of edges that are connecting to it. For example, in this graph, for the vertex B here, how many edges that are connected to B? We have from A, right? From A to B, we have from C to B, and from D to B. So in total we have 3 degrees. And normally the degree here is either an even or odd number actually, because sometimes there's one edge connecting to it, or sometimes there are more than one, or sometimes there is none because there is no relationship among them. And next we have a loop. Edges that are connected to the vertex itself. Example that from A here, if there is a line that there are loops, so this is they're connected to itself. And we have path are considering on the sequence of vertices such that adjacent pair of vertices are connected by an edge. For example, you have a path through here, right? Because this is a wrong direction, okay, we are not cover on this, and you may focusing on, okay, there's a path here, direction flow, okay. And we also have from A to C here, we go through A, B, then C, or we can say we can go A, then we go to D here, okay, and then we go to E, then we go to C. This is called the paths. And we have another term called multiple edges, when two nodes are that may be connected by more than one. For example, sometimes we have different weight. From here, they may use different method or something. Then there are two edges here. They are connected by multiple edges, or the direction can be inversed. And we have a simple graph, referring to the graph that are no loop at all and no multiple edge. Okay, this we can use in the terminology of the graph. And we have another thing, like in the degree, we can divide into 2 parts when we focus on the directed graph. In degree of a vertex, I is the number of edges incident to I. In here, referring to incoming edges. For example, degree number 2 here, how many incoming edge? This is from 1, right? Okay, it's from 1. So degree of 2 is 1. For the another point, we can focus on the number 7 here. Incoming edges, there are 2, right? From 5 and from 6 here. Okay, so degree of 7 is 2. And when we talk about the out degree, it's referring to the outgoing edges. For example, if you look on the edge number 8 here, okay, the vertex number 8, the outgoing is 2, right? 2 edges outgoing to 9 and outgoing to node 11. Okay, so there are 2 for the out degree of node edge. And next we will take a look on the graph representation. For graph to be computationally useful, we need to represent them in the program, and there are 2 commonly used methods for the graph representation, including the directed graph and undirected graph. We can use the method 1 we call adjacency matrix representation, which is used 2D array implementation. when we focusing on graph, firstly we count how many nodes it have, and then we will arrange the size of this array with the size of node here. For example, if we have 5 nodes, it means that our 2D array is 5 by 5, 5 rows and 5 columns. And then we will see its relationships. We can, if there is a line connected from one node to another, we will say false or we will say true if they are connected. And sometimes we just use 0 or 1. For example, in here, from 0 to 2, right? From 0 to 2. So we have the 0 here, 2. Okay, it is true, okay, because there is a relationship from vertex 0 to vertex number 2. And for another vertex from 1 to 0, as we can see, there is no relationship at all, right? From vertex 1 to 0 here, there is no relationship. So the value for this is false. Sometimes we just put 0. And in the case that we use the weighted graph, that we have the value on the edge, we just put the number in these relationships. If it does not has any relationship, we just put 0. Okay? But in this case, this is no weight at all, so we just put true or false here. So very simple in this array matrix representations. And the second method is called adjacency list representation, in which that we use linked list. Okay. Although it uses linked list, but it still has the array, which is array of linked list. As we can see from our lecture on the hash table, we represent to solve the collision problem, we apply the array of linked list, right? Each slot is a linked list. So in here it also have the array of linked list. We have many slots representing the number of nodes. We have 4 nodes here, A, B, C, D here. So it means that our array is size 4, and each array element here is considering as a linked list. Okay? So in this case, because it holds the distance, the weight, the edge here holds some weights. So from A to B here, we have the connection, and then there is some value, right? So in this case, we can say from A here to B, and we have the value here as well, which is representing as the weight. So when we create a data structure, the list, our list here, this is representing as a singular linked list. And our data, we have the nodes, and we also have the value of the weight. And we have pointer in order to connect to another one. So as we can see here, from node B to node C, we have connection as well, right? And the weight is 9. So in here we can say that from B to C, we have the connection here as well. You can see here from B, okay, B here is representing as a node, and then we go to A. Can we go to A or go to C? So this is the representation for node B. We have A, and the weight is H, and we also have from B to C here, which is 9, right? The weight here, which is 9. So you can represent this one elements of the array is representing by one node in the graph, and the other are the linked list connections for each node. Okay. So next, for the adjacency matrix, it's kind of square grid of Boolean values. We can put 0 or 1, or sometimes if we have weighted graph, we put the value of the weight inside the cell. And if the graph contains n vertices, which means there are n nodes, then the grid contains n row and n columns. Okay, so we just count the number of nodes, then we put them into row and column to construct a table. So for the two matrices, let's say number I and j here, the element at row I and column j is true if there is an edge from I to j, otherwise it will return false. Okay. This just describe the relationship. If there are connection, we just put true, okay, for an edge. So as we can see from the previous example, we have the connection from one node to another, and then we put true when there are connection from them. Okay, this is an edge 2 to vertex 1, right? So 2 to 1 here. Okay, we have a connection. Okay, so the value is true. However, from 1 to 2, we don't have any connection. That's why we got false. So because it is directed graph, there is the direction, right? 1 to 2, there is no relationships. So in our matrix representation, from row 1 and column 2, the value is false. And however, if we're focusing our attention on the undirected graph, for the adjacency matrix representation, there are two ways around, right? I mean, from 1 to 2 and from 2 to 1, they are connected. Example, in this case, from node 1 to 2 here, we have 5 nodes, right? Okay, 5 nodes. So it means that our table have 5 rows and 5 columns. And from vertex 1 to vertex number 2 here, there is a line, right? There is an edge. So it means that from 1 to 2, we got the value is true. So in here, just put, if you want a number, okay, just 0 or 1. But if it has a weight, you can just put the weight number. And from 1 to 2, we have 1, and then from 2 to 1, okay, there's also a line. There's because it is undirected graph. It means that from 2 to 1, we also have some value, okay, which is true. So we put it 1 as well. And so on and so forth for other edges that are connected to each other. Another example, like from 5 to 4, okay, row 5, and then column 4 here, we got a number, right, because they are connected. But if we focus on 5 and 1, okay, 5 and 1, there's no, right? Because vertex 5 here and vertex number 1 here, there is no connection. Okay? We must go from the path 5, 3, and 1. Okay? That's how we represent it. And for the adjacency matrix here, we also apply into the directed multi-graph. As we have discussed on the multi-graph, it's referring to the graph that have multiple edges, more than one, right? More than one. For example, from vertex number 1 to the vertex number 2, there are 3 edges, right? And in some cases, when we put some weight, okay, we may have different weights. Okay, that's how we implement it. And in this case, if there's no weight, okay, you just count how many edges that are connecting from vertex 1 to vertex number 2 here. We have 3, right? So we put 3 edges, okay, and so on and so forth. And for the other, and also have the loop, right? This is called loops. This node have from 3 to 3, we have 2 edges. They are loop, so we put 2 here. And regarding to the adjacency list representation, when a graph of n node here is represented by a one-dimensional array of linked list, so it means that array of linked list, where that each element in the array here, which is the linked list, so we access to L of E, it means that each element in the array, so array of linked list, each element in the array, because array we have many slots, right? As we learn from hash table, okay. So this also applies similar. We have many slots, and this is a linked list, okay, linked list where there are many elements will connect to each other. So the Li here is the linked list which containing all the nodes adjacent from I, and the nodes in the list Li here are in no particular order. We don't need to concern about the order, right? If there are connection for them, okay, just put whatever you want, whether you insert it to beginning of the list or end of the list for this particular slot, okay, that's fine. And as you can see on this example, we have the graph here, okay. We have 4 nodes, vertices here, therefore A, B, C, and D, and this graph is weighted. We have the number here. And if we make it into the adjacency list representation, because we have 4 nodes, so it means that our array have 4 slots. Okay, each slot represent 1 node, and then we will try to find the connection of this node to another in the graph. Okay, so as we can see that A, there is connection to B, A to B, and then A to D, right? So from A here, let's say the first element of the array is vertex A, and then the connection to B, we have some weight, right? Is 8. Okay, so you can put 8 here. It really depending on your data structure that you create. So this is a linked list. Okay, each element here is linked list, and then you can have the head and then insert begin or insert end depending on your implementation. And we also have from A to D, so here there's a connection. So remember, there is no particular order. You can freely insert to begin or end. And focusing on C, okay, C for vertex C here, there is one edge, right? Connect from C to B, so the weight is 9. Okay, so here the node C, we have the other nodes adjacent to C, which is B, and the weight is 9. Okay, so there are no more other adjacent nodes, so we just put it here. Okay. So it's quite similar to hash table a lot. So in here there's something that we can also take notes for adjacency list. For each the vertex, store a list of vertices adjacent to V. Okay, for example, adjacent of 1. Here, what is the nodes? I mean the list of vertices that are adjacent to this one. Okay, so here there are 2 and 3, right? So our notation is ADJ, which representing adjacent. Okay, adjacent of 1. Okay, we put 1 in the bracket here. Okay, the value is vertex 2 and vertex number 3, right? Because there's 1 here, they are adjacent to 2. They are the edge connect to other nodes, which is vertex 2 and vertex 3. Okay, so we got vertex 2 and 3 here is a store list of vertex which are adjacent to this one. Okay, this is and regarding to the graph representation, okay, focusing on this representation graph, we have whether we store a name of people, we store the location name, we store a character, we store a number, it's fine. It's just representing by our vertex, and in this case we need to count how many of them. Okay, so if we count them, okay, how many? There are 8 vertices. Actually there are 9, right? It's not 8, okay, because we count them from 0. Okay, so there are 9 here. 1, 2, 3, 4, 5, 6 here, 7, 8, 9. So there are 9 nodes. If we represent it using adjacency matrix, we have 9 rows and 9 columns to the array. Okay, and we can find the relationship among them by putting the boolean value 0 or 1, or we can just put true or false. Okay, when there's a relationship, there's an edge, the nodes are adjacent to each other. And we have the list representation. We focus our attention on this point. We can construct the list here representing this graph. Okay. Okay, I think that's it for the introduction. Actually, you can also check more for further detail on the graph representation. There are many methods that we can access to the data. For example, breadth first search or depth first search, and some other algorithm to solve some problem. So in here, as we can see so far, we have seen the term used in graph and also how we can represent our data in the graph. So the next function that you can explore and work with graph is to access to our data, and what method that we can use to access to our data quickly. We have many algorithms. maybe you can check more. And also we also provide some playlists. There are many possible method and algorithm that you can use, and you can take a look in more detail on it. We will not cover in this lecture because we only focus on the introduction. I hope you can get the foundation to getting started with Grab. Grab it involved with many application and many problem, and also involve many complexity, algorithm and theory as well. So thank you for your attention.